In this lesson, we're going to talk about reflection and refraction. These are properties of all waves, but we're going to focus on light waves. Let's take a look at a simulation. This simulation is again from PhET. Here's the URL, and we see a laser pointer that as I move back and forth, you can see the reflected ray here coming up. We'll get to this ray that's being transmitted and bent in a moment, but first let's just focus on this ray, which we call the incident ray, and the reflected ray. And we can see that the angle to this center line, called the normal, of the incident ray and the reflected ray is always the same. So here we have our plane surface and our normal, which is 90 degrees to it, and we had an incident ray and we had a reflected ray. And we always measure the angle of incidence and the angle of reflection from the normal. So this angle here would be theta sub I, the angle of incidence, and this would be theta sub r, the angle of reflection, and we saw that those two angles are equal to each other. We also saw a phenomenon at the bottom of the screen in the simulation where we had a transmitted ray that was bending relative to the angle of incidence. And that bending of waves when they enter a new medium we call refraction, and it occurs due to a change in the speed of the wave. Let's go back to the simulation. I've changed the media slightly. Here we've got a vacuum, and we can see that if we measure the speed of light here, we get 1.00 c, c being the speed of light in a vacuum. So light is traveling at the speed of light in a vacuum, because that's what we've got up here. But if we go down here to this medium and we measure the speed, we see that we're only traveling at 75% of the speed of light in a vacuum, because this is not a vacuum, it's a more optically dense medium. And you can see over here that it's water. And so when we do that, when we move from a faster medium to a slower medium, notice that this angle down here, 28.3 degrees, is less than this angle. So we have light that is bending towards the normal, meaning this angle is smaller than the angle of incidence. We'll call this the angle of refraction. In contrast, if I reverse that and I go from water into air, now I've got a slower speed up here compared to down here, and now notice that light is bending away from the normal, that this is a bigger angle from the normal than this is. By the way, notice that here it says air, and I'm alternately calling this medium air or a vacuum. The speed of light in air or a vacuum is, for our purposes, essentially the same. So when waves move from a fast medium to a slow medium, like we saw when we went from air into water, then we got an angle of refraction that was smaller than the angle of incidence. So we had a picture that looked a bit like this. In this case, theta 1, the angle of incidence, is greater than theta 2, the angle of refraction. So when we go from fast to slow, the waves bend toward the normal. In contrast, when we move from a slow medium to a fast medium, we saw the opposite. We saw that the waves bent away from the normal, so we had a picture that looked more like that. And I can call this again theta 1 and theta 2. Remember that we're always measuring between the ray and the normal. So slow to fast, waves bent away from the normal. To understand better why this occurs, let's switch to the wave model instead of the ray model. We've got a fast medium here and a slow medium here, and notice that as we move from the fast medium to the slow medium, we get bending towards the normal. Also notice that the wavelength decreases, the crests get closer together, because remember the frequency of the wave stays the same as it goes into a new medium, but if the speed is decreasing, then by the universal wave equation, to keep the left and the right side equal, the wavelength must go down as well. Now think of the wave up here, each crest consisting of people walking linked arm in arm, and they're moving from a fast area to a slow area. So you can imagine them walking from concrete into very mushy sand or mud. If they're linked arm in arm, the people on this end will enter the slow sand earlier, and so they will slow down, while the people on the other end are still walking on the fast concrete, and as a result the line will turn and they will end up walking in a different direction. Now at a certain point over here, they're all walking on the sand slowly, and so there's no more turning, and then they just progress down the screen. So you can think of that effect as analogous to what's happening here with the light. Also, before we leave here, just notice a couple of other things. First of all, the speed of light in a vacuum doesn't depend on the frequency. It's the same no matter what color of light I have. But that's not true in media that are not vacuums. So if I change this, you can see that at a certain point I get down to a slower speed as I get to higher and higher frequencies, shorter and shorter wavelengths, and the reverse. So speed is actually dependent on frequency. The speed of light is actually dependent on frequency in media other than a vacuum. Also, over here, notice that the index of refraction, n, is a way of talking about that speed. So if I change the medium and I change the index of refraction, the speed changes. As I get to a higher index of refraction, the speed gets slower. As I get to a lower index of refraction, the speed gets bigger to a larger fraction of the speed of light in a vacuum. So the index of refraction is a way of talking about the speed of light in that medium. So the speed of light in a vacuum C is equal to 3 times 10 to the 8 meters per second, or about 300,000 kilometers per second. And the index of refraction n gives us a way of talking about the speed of light in other media. And n is equal to c, the speed of light in a vacuum, divided by v, the speed of light in the medium. So n here, I'm going to write n sub medium, because that's specific to a medium, and this is v sub medium. So both the n and the v are specific to the medium, but the c is constant, and you can think of c as standing for constant. So if I want to find the index of refraction for a given medium, I take this number, 3 times 10 to the 8 meters per second, and I divide it by the speed of light in the medium. Or if I'm given the index of refraction, I can rearrange this equation to solve for the speed of light in that medium. And you can see that because v, the speed of light in the medium, is in the denominator, as we get faster media, faster v, then n is going to come down. So a smaller value of n means a faster medium. Also notice that we can never get an n lower than 1 because we can't get speeds of light faster than 3 times 10 to the 8 meters per second. So the biggest possible value of v would be this. We'd be in a vacuum, and n would be equal to 1. All other values of n are greater than 1, meaning that the media are slower to light than a vacuum is. Now that we've got the index of refraction, we have a way of quantifying how the angle of refraction relates to the angle of incidence. So here we've got a boundary between two media. I'm going to call this medium 1 and this medium 2. And we've got a ray that is incident on the boundary. We'll call this theta 1 and this theta 2. Again, remember, we're always measuring to the normal. So if this is medium 1, then the index of refraction of medium 1 is n1. And if this is medium 2, then the index of refraction is n2. And the relationship, the mathematical relationship between these is called Snell's law, and it tells us that n1 sine theta 1 is equal to n2 sine theta 2. Remember that big values of n indicate slow media, and small values of n indicate fast media. So let's say n is small, we have a fast medium, then theta is going to be big, because if theta gets bigger up to 90 degrees, sine theta will get bigger as well. So for this equality to be maintained, a small n will require a big angle, and vice versa. If n is big, meaning we have a slow medium, then theta is small. So if we look up here, we have a smaller angle to a bigger angle. We are bending away from the normal. So theta here is smaller. That means n must be bigger. Theta 2 here is bigger. That means n2 must be smaller. We are moving in the picture from a slow medium into a fast medium. Also, we could rearrange this to get n1 over n2 equals sine theta 2 over sine theta 1. And because n1 is equal to c over v1 and n2 is equal to c over v2, we can also get the expression v2 over v1. So n1 over n2 is equal to sine theta 2 over sine theta 1, which is equal to v2 over v1, v2 and v1 being the speeds of light in the two different media. And that shows us again that if n1 is bigger than n2, then v2 is bigger than v1, meaning if the index of refraction of medium 1 is greater than that of medium 2, then the speed is faster in medium 2 than it is in medium 1. So that's an introduction to reflection, refraction, and Snell's law.